Welcome. We are discussing our third chapter, Calculus of Vector Fields. We are now going to start our second module, Vector Derivative of a Vector Fields. In this module, we shall discuss vector derivative of vector fields as well as partial derivatives of vector fields. In this module, we shall study the notion of vector derivative of a vector field. This notion describes the rate of change of the concerned vector field with respect to an arbitrary vector. We shall also discuss the partial derivative of a vector field. This partial derivative describes the rate of change of the concerned vector field with respect to unit coordinate vector. We repeat that any vector has two characteristics, namely direction and magnitude. Let A and y be two vectors in Rn where we assume that y is non-zero. We define LAy to be the set of all vectors in Rn of the form A plus Ty where T is any real number. Then we can check that Lay denotes the straight line in Rn which passes through the point A and is parallel to the vector y. Let us now state the definition of a convex set. A non-empty set A subset of Rn is said to be convex if and only if whenever it contains two distinct points A and B, it also contains the line segment joining A and B. That is, if A and B are members of the set A, then the set consisting of the elements Ta plus 1 minus T times B, where T is arbitrary real number from the bounded closed interval 0 to 1, also lies in A. We know that any open sphere SAR in Rn is a convex set in Rn. Let A be a subset of Rn and A is an interior point of the set A. We assume that F from A to Rm is a vector field. Our interest is to study how the vector field F changes when we move the point A along a line segment to a nearby point A plus y where y is non-zero. Now, any point on the line segment joining A and Ay can be expressed as the form A plus Hy where h is any real number. Here the vector y describes the direction of the line segment. Since we assumed A as an interior point of the set A, there always exists some positive bar such that the open sphere with center at A and radius r lies entirely within A. So, for sufficiently small h, the line segment joining the points A and A plus Hy will lie inside the open sphere SAR and hence inside the set A. Now, we are in a position to define the directional derivative of a vector field. Later, we shall change the name. Let A be a subset of Rn, A is an interior point of the set A and F is a vector field defined on the set A where the codomain of F is Rm. The directional derivative of F with respect to the vector y at the point A is denoted by dyFA or f dash Ay and is defined to be the quantity limit of f of a plus Hy minus Fa by h as h tends to 0, provided the limit exists. One note here. We notice that A and A plus Hy both are in Rn. As f is a map from A to Rm, we have both Fa and f of A plus h are members of Rm. Therefore, the difference f of A plus Hy minus Fa is well defined and also it is a vector of Rm. We multiply this vector by a scalar 1 by h, obviously h is non-zero, and consider the limit of the entire quantity as h approaches 0. Whenever the limit exists, the resulting vector is denoted by f dash Ay and obviously it is a member in Rm. One remark here. The above definition is also valid if we put y equal to the 0 vector. In this case, the directional derivative f dash a theta exists, and moreover f dash a theta equals the 0 vector for every a from the set A. In the following remark, we now introduce the notion of partial derivative of a vector field as a particular case of the above. Now, in the definition of directional derivative of a vector field, if we take y equal to ei, that is the ith unit coordinate vector in Rn, for any I running from 1 to n, then the directional derivative f dash a ei is called the ith partial derivative of the vector field f at the point A and is denoted by difa. So, in this case we have f dash a ei equal to limit of f of a plus hei minus fa by h as h approaches 0. If we look at the numerator, in the first element there is only one change, that is in the ith coordinate. So, this is our known notion of partial derivative, and we have thus f dash a ei equal to limit of f of a1 up to ai minus 1, then ai plus h, then ai plus 1 up to an minus f of a1 up to an by h, which is nothing but difa, and this is true for every values of I from 1 to n. Now, one very important observation. In the expression for directional derivative f dash a y, let us replace the vector y by 2y, and we watch what happens due to this change. We assume that y naught is not the 0 vector. As a result, y and 2y are vectors in the same direction with different magnitudes. Then we have d2fa or f dash a 2y is nothing but limit of f of a plus 2hy minus fa by 2h. To balance, we have to multiply by a factor 2 and consider the limit as h tends to 0. So, we find d2yfa is 2 f dash a y after a short calculation. In fact, if we started with cy, where c is any real number instead of y, then we can find f dash a cy equal to c times f dash a y. This clearly indicates that the derivative depends on both the magnitude and the direction of the vector concerned. So, we prefer the term vector derivative instead of directional derivative to use in the remaining part of this module. One can easily recall that the same thing happened when we dealt with scalar fields. Also, from the relation f dash a cy equal to c f dash a y, we find that f dash is homogeneous with respect to its second entry. Next, we are going to see how the vector derivative of a vector field is related to the vector derivatives of its component functions. And a similar result will follow for partial derivatives also. The theorem, let A be a subset of Rn, A is an interior point of the set A, and F is a vector field defined on the set A whose codomain is Rm, and F1, F2 up to Fm are the component function of F. Then for some arbitrary vector y in Rn, we find f dash ay exists if and only if for each value of j from 1 to m, fj dash ay exists. Also in this case, f dash ay equals to the ordered m tuple f1 dash ay, f2 dash ay up to fm dash ay. This result helps us to study the vector derivatives of a vector field with the help of vector derivatives of its component functions. We give the proof. We have f dash ay. By definition, it equals with limit of f of a plus hy minus fa by h as h approaches 0. Now we write down the values of f of a plus hy minus f a in terms of its components. Then we can write this as limit of h tends to 0 of the following m tuple f1 a plus hy minus f1 a by h continued where the last term is fm a plus hy minus fm a by h. So, the value of this equals with the m tuple limit h tending to 0 f1 a plus hy minus f1 a by h continued up to limit h tending to 0 fm a plus hy minus fm a by h. So, this equals with f1 dash ay up to fm dash ay. So, this completes the proof. One corollary. Let A be a subset of Rn, A is an interior point of the set A, F is a vector field defined on the set A with its codomain Rm, and F1, F2 up to Fm are the components of the vector field F. Then for each coordinate vector Ei, we can find that DIFA exists if and only if for each j equal to 1 to m, DIFJA exists. Moreover, in this case, DIF at A equals with the m tuple DIF1A, DIF2A up to DIFM at A. Now, we cite some examples. Let f is a vector field defined on R2 by fxy equal to x square plus xy y square for every xy in R2. Now, we take an arbitrary point xy in R2 and an arbitrary vector uv in R2. Our target is to calculate the vector derivative f dash xy uv. So, we form the quantity f of xy plus h times uv minus fxy by h and consider its limit as h tends to 0. So, after some calculation, we find that this equals with twice xu plus xv plus yu twice yv. Therefore, the vector derivatives of the vector field f exist in every direction in R2. In particular, if we consider uv equal to the 0 vector, then f dash xy theta equal to theta in R2. Now, for any point xy in R2, we have d1f at xy, that is f dash xy 1 0. So, it equals with limit of f of xy plus h times 1 0 minus fxy by h and its limit as h tends to 0. We put the values of f and eventually we find the value of this limit equal to limit of h square plus 2hx plus hy 0 by h as h approaches 0. That is f dash xy 1 0 equals to, putting the values and calculating, 2x plus y 0. Similarly, we can find d2f xy, that is f dash xy with respect to the vector 0 1. We simplify here and we find that its value is x 2 y. Next example. Here we consider linear vector fields. Let f from Rn to Rm be a linear vector field so that we can express f of alpha x plus beta y equal to alpha fx plus beta fy for every xy in Rn and for every real values of alpha and beta. That is, in other words, f is a linear transformation from Rn to Rm. Then for any point x in Rn and any vector y in Rn, we find that f dash xy, by definition this is limit h tending to 0, f of x plus hy minus fx by h. In the numerator, we can apply the linearity property of f. So, it becomes fx plus h fy minus fx by h. So, fx and minus fx take care of each other. So, we are with f dash xy equal to limit of h fy by h as h tends to 0, that is fy. As a particular case of this, for any point x in Rn and for each coordinate vector ei we can write dif at x equal to f dash x ei equal to f ei. Now we shall deal with the vector derivatives of sum and dot product of two vector fields in the following result. Let A be a subset of Rn, A is an interior point of the set A and F, G are two vector fields defined on the set A. The codomain of F and G is in Rm. Now F and G are such that for a vector field y in Rn, the vector derivatives f dash ay and g dash ay both exist. We claim that the vector derivative of the sum f plus g also exists and satisfies f plus g dash ay equals f dash ay plus g dash ay. Now we give the proof. Since both f dash ay and g dash ay exist, we have the existence of the following limits. First, limit of f of a plus hy minus f a by h as h approaches 0 and limit of g of a plus hy minus g a by h as h approaches 0. Now we have f plus g dash ay equal to limit of h tending to 0 f plus g at the point a plus hy minus f plus g at a by h. So, we can write this as limit of h tending to 0 f of a plus hy minus f a by h plus limit h tending to 0 g of a plus hy minus g a by h, which equals with f dash ay plus g dash ay since both the above limits exist. This proves the desired result. Now corollary. Let A be a subset of Rn, A is an interior point of the set A, F, G are vector fields defined on the set A and codomain is Rm. Now, F and G are such that for each coordinate vector ei, the ith partial derivatives dif at A and dig at A both exist. Then the ith partial derivative of the sum f plus g also exists and is given by di f plus g at A equals with di f a plus di g a. Now another result. Let A be a subset of Rn, A is an interior point of the set A and F is a vector field defined on the set A whose codomain is Rm. F is such that for a vector y in Rn, the vector derivative f dash ay exists. Then for every scalar C, the vector derivative of the scalar multiple Cf also exists and moreover, Cf dash ay equals with C times f dash ay. One more result. Let A be a subset of Rn, A is an interior point of the set A, Fg are two vector fields defined on the set A whose codomain is in Rm. Now, F and G are such that one of them be continuous at the point A and also for a vector y in Rn, the vector derivatives f dash ay and g dash ay both exist. Then the vector derivative of the inner product Fg with respect to the vector y at the point A also exists and is given by inner product Fg dash ay equal to inner product of Fa and g dash ay plus inner product of Ga and f dash ay. Proof. First we assume that f is continuous at the point A. Since the vector derivatives f dash ay and g dash ay both exist, we have f dash ay equal to limit of f of a plus hy minus f a by h as h tends to 0 and limit of g of a plus hy minus g a by h as h approaches 0 both exist. So, we calculate inner product Fg dash ay. This equals with by definition limit of inner product Fg a plus hy minus inner product Fg a by h as h approaches 0. So, the numerator is inner product f of a plus hy g of a plus hy minus inner product f a g a. The denominator remains as it was. We simplify the numerator and we find that the value of this equals with limit of inner product f of a plus hy and g of a plus hy minus ga added with inner product ga with f of a plus hy minus f a by h as h tends to 0. So, this equals with inner product of limit f of a plus hy and limit h tending to 0 g of a plus hy minus ga by h plus inner product ga and limit of f of a plus hy minus f a by h as h tends to 0. So, finally, we have this equals with inner product f a g dash a y plus g a f dash a y since f is continuous at the point A. This proves our desired result. Now, one corollary here. Let A be a subset of Rn, A is an interior point of the set A and Fg are two vector fields defined on the set A whose codomain is Rm. We further assume that one of which f and g is continuous at the point A and such that for a unit coordinate vector ei, I runs from 1 to n, the ith partial derivatives difa and diga both exist. Then the ith partial derivative of the inner product fg also exists, and further it is given by di inner product fg at A equals with inner product of fa diga added with inner product ga dif at A. One remark here. Let A be a subset of Rn, A is an interior point of the set A and F is the vector field defined on the set A whose codomain is Rm. We have seen that if the vector derivatives f dash ay exist for every vector y in Rn, then in particular replacing y by the unit coordinate vectors, we conclude that all the partial derivatives difa exist where I runs from 1 to n, but the converse is not always true. We show this by an example. Let f from R2 to R2 be a vector field defined by fxy equal to ordered pair f1xy, f2xy, where f1xy is xy and f2xy is defined as follows. If either x equal to 0 or y equal to 0, then f2xy is x plus y, otherwise it is 1. Then we have d1f00 is the ordered pair d1f100, d1f200. We use the definition and after calculation we found that it is 0, 1. In a similar fashion, we calculated d2f at the origin and we found that it is 0, 1. So, the partial derivatives d1f00 and d2f00 both exist. Now, we choose any vector uv from R2 except the 0 vector and we find that f dash 0 0 uv. After putting them, we find that it is ordered pair 0 and limit of 1 by h as h approaches 0. We know this limit does not exist. Hence, this vector derivative of f does not exist. One remark. Let A be a subset of Rn, A is an interior point of the set A and f is a vector field defined on the set A whose codomain is Rm. We assume that the vector derivatives f dash ay exist with respect to every vector in Rn. But it may so happen that the vector field f is not continuous. We cite an example here. Let f be a vector field defined over R2 and codomain R2 defined as follows. fxy is the ordered pair f1xy, f2xy for every xy, where f1xy equals x square y for every xy not 2, and f2 is defined as follows: f2xy equals xy square by x square plus y4 if x is non-zero, and if x is 0 it equals 1. Now for any vector uv in R2, for u non-zero we have f dash 0 0 uv. We have shown here the calculations. This equals with the vector 0 v square by u. And for uv in R2 with u equal to 0, we find that the vector derivative f dash 0 0 0 v equals with 0 0. This shows that the vector derivative f dash 0 0 uv exists for every uv in R2. But this vector field f is not continuous at the origin because its second component function f2 is not continuous at the origin. So, in this module, we introduced the concept of vector derivatives of a vector field. We discussed its properties. With this, we conclude here.